So Travis, thanks for joining us. I wanted you to talk to us tonight about optimizing LLM inference on using Lorax, which is something that you guys came up with. I think it has a lot of potential and would love to hear from you about that. Travis, this is what I could gather about you, and please correct me if I got some of this wrong. You're the co-founder. I got one of my premier folks to join in too. Okay. You're the co-founder and CTO of Predibase. You were the lead maintainer on Horovod distributed deep learning framework within the Linux Foundation. You were a co-maintainer on Ludwig, which is a declarative machine learning framework using YAML, and then you led Uber deep learning training team as part of Michelangelo machine learning platform.
That's all correct. Yeah, definitely.
Awesome. That's great. And we're here today to talk about Lorax. So Lorax is, I'm going to try to explain it as much as I can, and feel free to fill in the gaps or correct me if you can, Travis. So Lorax is basically a framework that the team at Predibase created to allow people who want to deploy LLMs to load their foundation model once and then be able to switch the adapter layer however they want. And this mechanism will allow them to basically optimize the cost of serving, because they only have, if you need to load Llama 2 or Bloom, you only need to load it once. And then if your application is dependent on 3 models, they're supposed to be the fine-tuned models of Llama 2, you only load the adapter layer on top of that foundation model. Did I do it right?
That's all right. Yeah.
Okay, awesome. Well, I think I hope I gave everybody a general idea, but we'll hear what you got to say about this, and so take it away.
Awesome. Let me go ahead and get my slides pulled up. All right, should be good. Let's see. Can you enable the screen sharing, please?
I definitely can do that. Sorry for the who can share? All participants. How about now?
Let's see. And then I think it just needs you to stop sharing so that I'll have permission to share.
Stop share. Okay.
And there we go. I think we're good. Perfect. Yeah. Hopefully everyone can see my screen.
Yep.
All right. So yeah. Yeah, thanks for that introduction. So I'm Travis, and I'm here to talk about this framework that we wrote and open sourced late last year called Lorax. Allows you to serve hundreds of fine-tuned LLMs on a single GPU through loading the adapter layers dynamically, as was mentioned. And it can even scale, beyond that to potentially thousands of adapters, thanks to some offloading things that we do. But we'll get into some of those details a bit later on. I think one thing I always like to start off with when we do these presentations is talking a little bit about before we get to that, talking about why this project exists, and it basically comes down to the fact that at Predibase, we started the company as kind of a training platform for deep learning models, and that's become over time like really focused on fine-tuning large language models. And one thing we very quickly realized as we started doing this is, man, this is going to be really expensive to serve all these models. If you just do it like with one GPU per fine-tuned LoRA, right? And so that led us to start thinking about ways that we could optimize that and kind of leverage the fact that these parameter efficient fine-tuning techniques like don't modify all the parameters. And so we'll get into a lot of the technical details. This presentation is actually pretty light on kind of the user-facing component of it, because I think that stuff is pretty, it's in the docs, it's in the README, so hopefully it's pretty accessible. But definitely want to get deeper into the weeds of how this actually works and how he implemented it, and give you a sense for, what motivated some of the decisions we made. So the first thing I'd like to do is set the stage a little bit about why we're here talking about large language models in the first place. And I'm sure you all, are pretty familiarized with LLMs at this point. But definitely, I think it's worth just noting that if you look at the history of machine learning and also deep learning over the past few years, it's definitely been driven in large part by the advent of these like bigger and more powerful and more general LLMs, starting with things like BERT, early transformers-based model, GPT-3, all the way up to now with GPT-4 at the estimated to be in the trillions of parameters. Definitely you could draw a conclusion that this has all been driven by bigger and bigger models giving us more and more capabilities. But one thing that we think about a lot for my company, and I think this is broadly true for a lot of people as well who are interested in using LLMs, is that while it's great that these models are getting more and more general purpose and can do all these different things, that's actually not needed in a lot of cases. Like usually when you're using an LLM, you're using it for a very specific purpose, like you're wanting it to generate a certain type of text, or structure things in a certain way, or classify certain documents. Certainly there are like very open-ended chat applications as well, but even in those cases, you're usually restricting it to a certain type of conversation that you want to have, and not wanting it to kind of go off the rails and talk about something unrelated. So one thing we like to say is, general intelligence is great, but I don't need my point of sale system to recite French poetry. So really you want a model that's, kind of fit to purpose, right? Like big enough to do the task, but not so big that it can do everything, because one way or another, you're paying for that, right? So what we like to say is that when people think about using LLMs and getting value from them, putting them in production, or, using them locally for your own purposes, that it's often very practical to start with these general purpose APIs like GPT-4, which are good for building prototypes and getting a sense for like what is the art of the possible in terms of what these models are capable of. But in practice, like once you start getting serious about this and you're realizing this is something you want to run, 1,000 times an hour or every day, right? That they're very expensive, slow, and overkill for most tasks. And for some users, the fact that you have to give up access to your data because you're sending it over the network for every request can be an issue. And also the fact that ultimately the model, you don't have any control over it. It's not yours. They can update it anytime they want and break your application, right? If they decide that, the kind of thing that you're trying to do with it is against their terms or not what they want you to be doing with it. Or even accidentally if they just, make a parameter change somewhere, right? So there are definite risks to kind of attaching yourself too strongly to closed source APIs. So the alternative view of the world that we ascribe to is this idea that you should be building specific models for the specific tasks that you're trying to solve with LLMs, rather than just relying on these big closed general purpose models. So for example, like let's say you're an organization out there that wants to productionize LLMs. You might have a Mistral 7 billion fine-tuned model that's only used for prioritizing customer support tickets. You might have another model like a Llama 2 70 billion fine-tuned that's for customer service chat. Or you might have a even simpler BERT model for sentiment classification, something like that. And the benefits of these task-specific LLMs is that they're smaller, cheaper, and faster. You can also control the output much more strongly through fine-tuning, the fine-tuning process itself. You don't have to share your data. This can all run locally or run in your own cloud. And it's ultimately a model that you own and you can do whatever you want with, and you can control when it gets updated. And I think that there are really practical and observed benefits to doing something like fine-tuning as well. Like it's not just a matter of, yes, it's cheaper and open source and whatever, but it's not as good. Like I think that it's definitely the case that a good fine-tuned model for a specific task can outperform even the best general purpose models like GPT-4 by a significant margin. And so here's just a really simple example is, we fine-tuned Llama 7 billion, not even the biggest one, on a very specific JSON extraction task. And that fine-tuned model was significantly better, 40% more accurate than even GPT-4 at like a, multiple orders of magnitude smaller footprint, right? So there are definite reasons why you'd want to do something like this if you care a lot about, this particular task. And we also believe that a lot of people are going to find that they don't just want to train one LLM, that they often want to train many LLMs. As I mentioned earlier, like our motivation at Predibase for this was, building a platform that supports many different customers that all want to fine-tune LLMs and thinking, wow, how are we going to serve all these models, right, in a serverless way? And that was kind of the main motivation for us. But once we built it, we realized that there was a lot of value there for potentially, other people as well. Like when I was at Uber, we trained a lot of what we call segmented models, where it was the same task, but it was segmented by maybe the user or the product or the region. So you can often get into these situations where you want to train the same model, but on different slices of the data, right, for that extra level of personalization. And also, I think, a lot of people, particularly in maybe the local LLM community, are interested in, agents and workflow-based systems, the kinds of applications that got people really excited about LangChain earlier on. And as you think about these individual agents or tasks that you want to do, oftentimes they're very specific, right? You maybe want it to like do some retrieval step, or, maybe you want to do some kind of routing step to determine what path to go down, right? And in those cases, having specialized models at each point in those workflows gives you better performance. And if you can run them all in a single instance, that's going to make it very cost effective for you. But the challenge, of course, is the cost component without something like Lorax. And so, one example here is just looking at how much, these types of GPUs tend to cost if you were to rent them. Obviously, if you're in the consumer tier, you just buy it once. But oftentimes people that, are looking to productionize LLMs are thinking about how much it's going to cost in GPU hours to AWS, for example. And just to take a simple example, like let's say we want to serve a model on something equivalent to an H&G and rent it out from AWS at $1.21 USD per hour. How much is that going to cost? And you see that as you scale up the number of adapters, assuming that every one of these is its own deployment, you're very quickly talking about, at even a relatively small number like 16 LoRa's, you're talking about, close to $15,000 a year, which is quite expensive, or per month.
Travis, just a question about this. In this model, you're talking about loading, when you're talking about loading the adapter, in this model, you're loading the foundation plus the adapter multiple times. Is that correct?
Yes.
Okay.
Yeah. So that's the naive version here that I'm illustrating. Yes. Yeah. So yes, exactly. So to that point, if you were to be loading the foundation model plus the adapter in its own deployment every time, you're very quickly talking about like tens of thousands of dollars per month to serve that. So parameter efficient fine tuning. Let's talk a little bit about this particular part of the concept. So in traditional fine tuning, you have a data set, you have a pre-trained LLM, and then you're going to update all the weights of that model. But in parameter efficient fine tuning, which is primarily what we're interested in for the purposes of talking about Lorax, what you want to do instead is take your pre-trained LLM, the foundation model component, add a few additional fine-tunable parameters, and then only train those small parameters, so that what you get at the end is your foundation model plus this very small portion of new parameters that go alongside it and specialize it to the particular task. And one of the most common techniques that we see in practice for this is low rank adaptation, also known as LoRA. And the nice thing about LoRA is that you can kind of insert it at almost any in particular linear layer in your model, where you have some weight matrix that here is going to be assumed to be D by D, where D here is the hidden size at this particular layer. And what you're going to do is just insert these two additional matrices alongside that pre-trained weight that are low rank, meaning that they're hidden dimension by some small number and then some small number by hidden dimension. And the nice thing about this is that when you multiply these two matrices out, they give you the original shape, but at a footprint that's like around 1% of the size of the original matrix when fully expanded out, right? And so what that means in practice is that you have a very small checkpoint that you're saving out when you do this fine tuning, and then you have a very small delta that you load in when you want to do inference. And so this brings us this idea of, well, could we use this in some way for a parameter efficient inference solution for these LLMs as well? So let's talk about that. So here's the anatomy of a fine-tuned LLM deployment without Lorax, which is that you have some pod, or you can think of it as a node like your local machine, that is containing the model parameters here, which are orange. You have some request queue that sits in front where the user is sending the request saying, hey, generate a response to this question, et cetera. And then you have these adapter weights that are loaded in alongside the original weights that specialize it to a task. And so, if you were to do this, again, the naive way, every time you want to load a new LoRA, you spin up a new deployment. And, assuming you have multiple GPUs on your machine, you can do this to some point. But eventually you're going to run out of GPUs, or you're going to just have to pay AWS a ton of money to keep scaling up, right? So the realization here is that these weights, the foundation model weights, the orange ones, are exactly the same between these models. So, hey, can't we just serve this all in one deployment and then only load in these adapter weights dynamically? And so that's exactly the motivation behind Lorax that we're now going to get into. So effectively, Lorax is an LLM inference system for fine-tuned LLMs, and consists of three components that I'll talk about. The first is what we call dynamic adapter loading. That's the ability to load these adapters on demand when the request comes in. Heterogeneous continuous batching, which is an extension to the popular continuous batching algorithm that allows you to mix requests for different adapters together in the same batch. And what we call adapter exchange scheduler, which allows you to decide which adapters should be batched together at any time to optimize the overall throughput and latency of the system, and decide when particular adapters should be moved from GPU to CPU in order to avoid out-of-memory errors and things like that.
Just one question here, Travis, about so when you talk about heterogeneous continuous batching, you basically group in a couple of requests that came from different users, for example, all asking the model for a response, and then you basically just couple that and then send it as a batch to the model.
Yes, that's correct. So, and the nice thing about the way that we do this is you can, each of those requests could be for a different adapter as well, right? So, and without having to sacrifice on throughput or anything. And so that'll be one of the things we'll get into in a bit, but I think it's one of the things that a lot of people are surprised, I guess, that we do, is they think that we switch the adapter every single request, but we actually don't. We can do them simultaneously. So dynamic adapter loading is the first idea, and it's exactly that first concept that I wanted to illustrate from the previous slide was, can't we just merge all these adapters into one deployment? And so that's effectively what dynamic adapter loading allows us to do, is every time a request comes in, so here we have a system that already has requests for blue and red adapters, and now we have this green adapter request that comes in. So what the Lorax system is going to do is go ahead and fetch that adapter from wherever it resides, whether that's in Hugging Face or in Predibase, we have our own model repos, or even your local disk or S3, something like that. It'll go and find the adapter, load it into memory, and then allow the request to get processed. And one of the nice things about the way we implement it is that the loading happens in the background, so it doesn't block any of the ongoing requests from completing. But instead, what will happen is once the adapter is loaded, then it will be eligible to start being processed by the system. And so at that point, it'll kind of join the other adapters and be able to start batching together for the requests. Now, to make this scalable, we implement what we call a multi-tiered weight cache for the adapters, because as you might imagine, at a certain point, you're going to reach the limits of what your GPU can hold in memory in terms of adapters. So what we do is we separate into 3 different tiers. The first is what we call the active tier, which is the adapters that are actually living on the GPU. And so therefore, they're the ones that the scheduler will say, yes, go ahead and accept requests from these adapters because they're already loaded on GPU. So we know that the response will be very fast. But for the other adapters, they live on the CPU or in the host memory rather. And those adapters, we call it the pending tier because they have requests that are sitting in the queue. And what will happen is at some point, Lorax will decide, hey, this adapter has been active for too long. Let's go ahead and move it to the pending tier and then exchange in another adapter that can go ahead and reside on the active tier and start accepting requests. And that's where the name, the LoRA Exchange system comes from.
And this algorithm that decides what adapter to move to the CPU or the disk, that's intrinsic internal to Lorax. That's something that you guys put together.
Yes, exactly. So that lives inside the Lorax system itself. And I'll walk through an example of kind of how the algorithm works in practice. But yes, it's specific to Lorax. And then finally, we have what we call the idle tier, which is essentially the adapters that are not in use at all right now, but maybe were, in the past, like maybe an hour ago. And so what Lorax will do in these cases is if it's for whatever reason running out of space and host memory, it'll just evict them, but then keep the adapters around cached on local disk, assuming that they were coming from, a cloud storage system of some sort. So they can be loaded in next time a request comes in. The heterogeneous continuous batching, I think, is one of the more interesting things that we do. The original implementation is shown here, but I think it does a good job of illustrating the kind of concept pretty well, which is that you have a batch that consists of some blue adapters and some red adapters. And instead of breaking these out into 2 separate batches, we process them at the same time. And then we have a parallelization process or algorithm rather that will take the weight matrices for the LoRa's that apply to the blue adapters and apply those weights to those inputs. And then similarly for the other adapters, apply only those weights to those inputs. And then they can get summed together as usual and then get forwarded to the next layer. So conceptually, it looks like something on the right, which is that you have the base layer, and then for every adapter layer, you're going to go ahead and conceptually mask out only the rows that apply to that adapter, and then go ahead and apply it, and then add that to the output. Now, this was actually the original implementation for Lorax, but the nice thing about being in this industry is that lots of innovation comes out of the research community as well. And so there was a really popular alternative to this strategy called the segmented gather matrix vector multiplication, or SGMV method, that was put forth by the authors of a paper called Punica, some researchers out of University of Washington. And their approach was to essentially write a custom CUDA kernel that allows you to parallelize, like basically this for loop right here, to parallelize this at the CUDA level, so that all this stuff can happen at once without having to dispatch, each of these operations separately, which, as you can imagine, will, start to slow things down as you start talking about many of these adapters need to be processed at once. So SGMV was open sourced in the Punica project, and we integrated into Lorax. And so now that's the primary way that we do the multi-adapter computation within a single batch. So I'll show some benchmark results on that a bit further down that kind of show you the comparison of the looped implementation versus the SGMB implementation. But before getting there, I wanted to talk briefly about the scheduler that I alluded to before. So the basic idea of the scheduler is that it's going to maintain N adapters as active on the GPU at a time, and then batch requests from the active adapters together by timestamp in kind of a first in, first out way, and then apply LoRa weights during the forward pass and conceptually mask out the rows as we showed before with the heterogeneous continuous batching. And then after some time t has elapsed, which is what we call the cycle time, then it's going to go ahead and do the exchange step where we swap out the oldest active adapter with the adapter that's been pending for the longest. And this parameter t that controls the cycle time is a really useful hyperparameter to play around with. So the higher, and I should point out that this only really matters at like an extremely high scale when you're talking about like literally hundreds of adapters, maybe even thousands, because at the low level of adapters, like up to 128 on, most cards, you can actually fit all of those on GPU pretty easily in most cases. But regardless, at a certain point, you can imagine that you'd run into this problem. And so what you can do is play around with this value t to prioritize either optimizing the overall throughput of the system or optimizing the latency of the system. So the higher value of t, that means the longer an adapter will sit in the active state and be able to accept requests before being exchanged out. Whereas a lower t value will swap adapters more frequently and therefore try to minimize the kind of worst case latency. But it's worth just bearing in mind that that is a trade-off at a certain scale that any system to run into.
This parameter here is something that is exposed by Lorax. So if in the Lorax, I haven't used it to be honest with you, but is it in the Lorax configuration that you could go and play with this parameter?
Yes. So there is a parameter called on the command line that we call cycle time seconds. And so that's this parameter here. It defaults to 2, I believe. So if we're at the limit of how many adapters we can fit on the GPU and a new request comes in, then it'll wait 2 seconds for the current set of adapters before doing the exchange. So that's the default behavior. And yeah, then the last step is just basically offload any idle active adapters if there are adapters that are pending. So basically, we don't want to have adapters sitting in the active state if they're not doing anything, right? And there are other adapters that are waiting to take their place. So we will go ahead and backfill adapters from the pending queue if we decide to evict the idle ones. So just as a quick illustration of this, here's how things will work. And again, this is a bit of a toy example because with 3 adapters, they all fit on GPU memory most likely, so you wouldn't, have to do any swapping. But for the purposes of illustration, let's assume that, these are very big adapters, I guess. So we have 3 adapters, A, B, and C, and our limit of how many adapters we can fit on the GPU is 2. So A and B, which were the first adapters, based on timestamp here, so this number is the timestamp, are the ones that are active first, right? And so adapter C here, which came in, its earliest request was at timestamp 4, is going to be in the pending state. So initially the scheduler sets A and B to active. In the first step, the scheduler goes ahead and fills in the batch, which is here on the right, first in, first out based on the timestamp of the requests in the active queues. So in this case, 1 from adapter A, and then 2 and 3 from adapter B. Next, we now reach a state where B is empty, but an important thing to note here is that we can't actually swap out B yet because it still has requests in the queue that are being processed. And so this is an important point when thinking about how the system works, is that we don't ever want to swap out adapters that are that still have requests in the queue or rather in the batch, because if we were to do that, then, if we move C to active, we still have to keep B as active in order to keep processing it here, which could potentially result in an out of memory error. So what we do instead is we keep B in the active state, but we don't allow it to accept any new requests if it's reached its time limit, right? Which it hasn't yet in this example, but that's something that we'll show in a moment. So at this point, all of B's requests have completed. As you see, we just have request 5 still in the batch. And as a result, we go ahead and move B to the idle state, and C becomes active. So this was an exchange step that occurred. And now C is going to start accepting requests into the batch as well. And so now, again, based on timestamp, we have requests 5, 4, and 6. And again, the reason why 5 was put on the batch before 4 is because B was active while this queue was still impending, right? So at this point, new requests are coming in, and once again, B is in the pending state, so it's wanting to become active. And the cycle time now has been reached. So what we're going to do is we're going to say, hey, adapter A has been on in the active state past its cycle time, and there's another adapter waiting its turn in the pending state. So now let's stop accepting any new requests from A, wait for its last request to complete. And then once it completes, we go ahead and move it to idle, and then exchange A and B so that B once again becomes active. And this process essentially just continues in perpetuity until, eventually the whole system becomes idle, right? All right, so now let's talk a little bit about how this does in terms of throughput and latency. And the good news is that this actually scales quite well in practice. And in particular, if you compare the loop implementation of the heterogeneous batching that I showed before with this SGMV kernel implementation that I talked about, what you see is that we essentially have very little, if any, degradation in throughput, even at 128 adapters in a single batch. So this is like under very, very heavy load, right? We're basically just hammering the system with as many requests as we can. And we see less than about 10% degradation versus one adapter. And then similarly for latency, if you look at the orange line here, this is the non-loop implementation. So this is the SGMV implementation. You can see that latency, is basically flat over time as we increase, or over the number of adapters. So as we increase number of adapters, latency stays more or less the same, very, very negligible increases. Versus the original looped implementation, we see that there's a linear increase in latency, which indicates that it's actually quite inefficient. Right?
I'm really impressed. Just out of curiosity, Travis, when you say 125 adapter or model that you load, what kind of GPU do you guys do this on?
So this particular benchmark was done, I'm trying to remember what I benchmarked it on. I think it was on an A100 with 40 gigabytes of RAM. So it was a pretty respectable GPU.
Okay.
But I've also run similar benchmarks on, closer to commodity GPUs like A5000s and A10Gs, and we see a similar effect. You can actually see a similar effect even if you run it on a CPU and you compare this particular algorithm versus this algorithm, right? But obviously that only works with very, very toy models, right? So the algorithm itself, the vectorization, is what's giving you that benefit. But definitely better hardware will let you do this with, bigger models and, more bigger LoRas as well.
Oh, it's amazing. It's great. You guys haven't had a chance to test it on any consumer GPUs like the 4090 or A6000?
So we have tests on A6000. Yeah, so we do have a few of those in our servers, our on-prem servers. And yeah, we haven't published any benchmarks on it, but we definitely see very similar effect here. But yeah, haven't run any tests on RTX like 4090s or anything like that. I have a 3080 myself, so maybe I'll like run a few tests on that one.
No, that's amazing. I like it.
And then I think cost is also at the end of the day, cost is really what we care about the most for our purposes. And so just to kind of illustrate how this translates into cost per million tokens generated, again, assuming that you're renting a GPU per hour and you're trying to basically see, how long does it take me to generate 1 million tokens, right? Then the really, I think, magical thing about Lorax versus spinning up a dedicated deployment per fine-tuned model is that we essentially see that as you add more and more adapters, I think OpenAI is pretty expensive for relative to most other players, but even at like less than 32 adapters, dedicated deployments per fine-tuned model very quickly become more expensive than OpenAI, and this just keeps on growing linearly over time, right? Whereas with Lorax, you can keep adding more and more adapters, up to 32, 128, and beyond, and barely notice any increase in the amount of time it takes you to generate, however many tokens you're trying to generate, which translates directly to your cost, your total cost of ownership, right? So total cost of ownership stays essentially flat even as you layer on more adapters. Couple of last things to round out is just a few other optimizations that we have. So there's a tensor parallelism for people who have multiple GPUs on their node. This algorithm came from another paper from academia called LoRA, which was similar to Punica, came a couple months later. They released this algorithm in their paper. Interestingly enough, they didn't actually implement it in their code, but this diagram was useful enough that I was able to reproduce it in Lorax. And so we do support multi-GPU with the multi-LoRa heterogeneous batching as well. So that's a feature for those who want to link together multiple cards, in cases where the model's too big to fit on a single card.
And that's natively supported by Lorax. It's a latest release that you guys have on GitHub does support this.
Yes. So if you have like 2 GPUs on your device or on your node, then you can just run it with all GPUs visible, and Lorax will automatically shard the parameters across the GPUs and then use this algorithm to make sure that the results are consistent. And then finally, just talking briefly about how we kind of fit this into, this is probably less relevant for folks running locally, but just talk briefly about how we fit this into kind of an overall serving architecture. We have in our system an API gateway that then requests flow through to like a load balancer that then distributes across different replicas. And this runs on like a Kubernetes cluster. And then the weights are backed by some system and object storage. And so one interesting thing about this that I want to call out is how you load balance across these replicas. It's kind of an interesting problem. And so one thing that we've been exploring to solve that problem of how you most efficiently distribute load across multiple different replicas of Lorax. One thing that you kind of quickly realize is that it's better to send all the requests for the same adapter to the same replica, because that will allow you to avoid having to reload the adapter multiple times, but it will also prevent you from getting into those situations where you have to do a lot of adapter exchanging, where you're swapping them out between GPU and CPU memory, and will just generally give you, better throughput overall. So one thing that we're looking to add to Lorax in the near future is this load balancer that provides a consistent hashing, where you basically say, look at the adapter ID for the request, and then hash it in such a way that all requests for the same adapter flow to the same nodes, to prevent this situation where all the nodes are loading redundant copies of the adapter. So what's next? A few things that we're currently working on, and I think some of this has actually changed recently, as the space continues to evolve pretty rapidly. But a couple of things that we've had on our backlog have been better memory right sizing, so that we know exactly how much memory we want to allocate for the pool of adapters, without any kind of possibility for users to have to play around with those values by hand. The SLORA paper that I mentioned has a really good implementation of a kernel for multi-rank SGMV. So basically being able to support adapters in a single batch that have different ranks. We support that as well, but we do it in a bit of a loop implementation. So we run a separate kernel for each rank. So being able to do them all at once, potentially a little bit faster. More types of adapters. I think we talked a lot about LoRa, and LoRa is a very useful adapter, but there are actually others that are very interesting as well, like classification adapters. So you can have a multi-layer perceptron that just limits the response to like one of a handful of outputs. Medusa is one that I think is very interesting, that lets you fine-tune a model to do speculative decoding, so you can speed up the inference process. That's one we're actually adding very soon. We got an ongoing PR in progress for that. More generality, so being able to expand to new types of architectures. Currently, we support Llama, Mistral, Quinn, GPT-2, Phi, probably Bloom, a few others I might be forgetting at the moment, but those are the main ones. There's been a lot of interest in supporting diffusion models for image generation as well, being able to support different types of layers beyond linear layers. And then also, I think one I'm very interested in is embedding models. So being able to fine tune a small adapter on top of an embedding model to customize the embeddings for like a retrieval augmented generation process. That's one that we're interested in as well. And then
that's a very interesting point, Travis. Honestly, I've always just used whatever was available when it comes to embedded models, just so I can do the vector database indexing. But do you see that happening a lot? People going in and fine-tuning embedded models?
So that's an interesting one, because I actually think not a lot of people do it today, but I do think that that's something that would give people the most bang for their buck when it comes to trying to improve the quality of their RAG applications. And we have some, we know the folks at Llama Index, for example, and have chatted with them about this in the past. And they told us, like, from all of their experiments, that the embedding model ended up being the most important thing to improve when wanting to improve RAG results. So definitely, I think you can get a lot of value if you have a unique data set in particular, by fine-tuning a model to improve the quality of the embeddings that you generate to do retrieval. Yeah, actually, one other that I didn't call out here that we're working on, this actually, my colleague told me they just got it working today, so we're hoping to land it like in the next couple of days, is support for outlines. If you don't know that one, it's a framework for doing constrained decoding, where you can basically give an LLM a JSON schema and say your response has to be in this format, and it will for sure guarantee that it'll be in that format. Or supporting things like function calling, where you say, here's a list of functions and their signatures, output only a response that contains the function you want to call and the arguments that you want to pass to it. So those types of applications, I think, are really useful for building agent-based systems and workflows. And so
yeah, this is mostly in the case of if you're thinking plugins, for example, if you have an agent that needs to do a lot of actions, and he needs to pick which actions to do depending on the request.
Exactly. Yeah. So we that was, I think, the most commonly requested feature for Lorax. So we ended up prioritizing that one, and should be landing very shortly. So pretty excited about that one. And then I see there were a couple of questions. So is this approach an alternative for RAG, LLM plus RAG, or lane chain architectures? I see it as really complementary. If you're using lane chain and you want to have a lot of different agents in your system that all do different things, if every one of those agents is a LoRa adapter, then it makes perfect sense to use something like Lorax to serve as the kind of endpoint that you're querying through lane chain. So I definitely think there's a very natural synergy that exists there. And then is the load balancer is via continuous hash or Kate's namespace based. So the load balancer, well, I would say candidly it doesn't exist yet. We're still working on it, but from the research we've done, we've looked at, so we use Istio as our service mesh for networking as well in Kubernetes, and they do support a consistent hashing algorithm for load balancers, and so we've been exploring using that, extracting out the adapter ID from that and doing consistent hashing based on that. And then agent is a LoRa adapter. Can you elaborate on the difference? Yeah, so I think that, there's certainly one view of the world where your agent is, like every agent in your system is going to be a certain prompt to an LLM, right? Like saying, hey, you're an agent whose job is to, go and order pizza, or you're an agent whose job is to classify this request into one of 5 different categories, things like that. And, in that case, you can think of the agent as kind of being like a bundle for a prompt template, right? But I think, one thing that's potentially very valuable is if instead of just using a single base model and then purely trying to improve the quality of your agents through prompt engineering, you could actually fine tune each of your agents in your system to be very good at whatever its specific function is, right? To be like, I'm the best agent for classifying this request, or I'm the best agent for knowing what pizza toppings to choose when ordering pizza, right? And so in those cases, you can imagine fine-tuning a LoRa for every one of those agents, and then using something like Lorax to serve all of those different LoRas together, so that even though you might have 100 agents in your system or whatever, they're all running on the same foundation model backbone, they're all running on the same GPU, and therefore, even though you're getting really, really good quality from them, you're not having to spin up like separate deployments for every single one of these agents. It's all running on one system.
Yeah, I think this is a really good case for, this is making the case further for fine tuning. I know this is an ongoing conversation, fine tuning versus RAG, but if you lower the cost of using the fine tuned model, I personally, this is personal opinion here, fine tuning for me has, gave me better results than RAG multiple times. So if you can lower the cost of fine tuning, you're probably making the case for just, if I can run 100 of my fine-tuned models, I don't necessarily need to do RAG and just get, those not very satisfying results. See what I mean?
Yeah, absolutely. I think that that's something that we see a lot as well is, there are definitely times where something like RAG or prompt engineering is useful. And then there are times where fine tuning is useful. And then I think there are also times where you can use them both together. Like you can fine tune models to be better at RAG, be better at generating text, or be better at, generating embeddings in the case of the embedding model. But definitely, I think we've found that, you can get quite a big lift when you go ahead and fine tune a specific adapter for a specific task, above what you can get with just prompt engineering. And I think a lot of the literature kind of backs that up, that, if you do have the data, and I think that's always the hard part, is getting the data to do fine tuning. But if you have good data, then you can definitely get a lot of value from fine tuning above what you could do with just prompt engineering and RAG. So to sum up, don't do this. Use Lorax instead. Put all your adapters on one base model, and things will be a lot easier for you. And finally, call to action here. Please definitely check out Lorax on GitHub. It is free and open source. We forked another project out there that some of you may be familiar with called TGI from Hugging Face back in August. So they changed the license from Apache to this new type of license that doesn't allow you to, use it commercially. But when we created Lorax from their foundation, we retained the original Apache license. And so all of Lorax is, free to use commercially as you want. You can do whatever you want with it. So please definitely check it out. feel free to contribute, give us a star, etc. Yeah, let us know if you have any issues.
Amazing.
And happy to stick around and answer more questions as well if there are any.
Yeah, we have a couple more minutes before we close. I'm happy to take any question from my folks here. Matt from Maven Code, or Daniel, if you have any questions. My teammate Ram is here too, so feel free to ask any questions.
Cool. So hopefully self-explanatory. I did see there was one other comment on chat. So I thought that adapters are already fine-tuned. Yes. So once you have the adapter, that's like, I guess maybe just taking a step back to like, what is the process here? So yeah, you start with your base model, and then you fine-tune the adapter for a specific task. Like again, in our example, like ordering pizza or something like that. And then you have this adapter that consists of just a handful of parameters. And then that's the thing that you go ahead and load with Lorax. So yeah, there is like a step that comes before Lorax that is implicit that, we didn't call out, which is you actually have to go and do the fine tuning. And there are, other tools that can help you with that. Like we have a project, another open source project called Lorax or Ludwig that helps you with that. There's Peft, Axolotl, things like that. But once you have the adapter, then yeah, Lorax is what we call a parameter efficient inference system for helping with that. And then is adapter management versioning external to Predibase? So yeah, for adapter management, we would recommend, there are a few different options. You can use Predibase as one option. We do have a model repository similar to Git. Hugging Face, of course, has model repositories as well that they actually use Git LFS under the hood, so they really are purely Git based. Definitely there are other options. I'm not familiar with what Snowflake offers in terms of versioning for files, but we do support S3 or local file paths as well. So you can imagine using, like, you could roll your own Git LFS solution, for example, and then just pull the repo and then load it locally to be able to deal with that if you like as well.
Awesome. Well, Travis, thank you very much. That was very useful. I'm definitely I have projects internally that could actually benefit from this in my organization, and I'm sure we'll be coming back to you for questions.
Awesome. Yeah. Well, thank you so much for inviting me to speak to you all today. And I hope you all enjoyed it. And yeah, please try it out. And we're pretty active on GitHub and on our Discord. So if you have any questions or if anything's not working right, just let us know. We'll definitely help out and see if we can get those issues resolved. So thank you all.
Awesome. Will do. Thank you all. Have a good night.
All right.
Bye.
Thank you. Thanks, guys. Thank you.